So let's look at the acidity of acetylene and terminal alkynes. So we're looking at this hydrogen right here. Let's do a nice green color. That hydrogen right there. And we find that it has a pKa of 25. For the ethylene, the hydrogen in the same position has a pKa of 44, and for ethane, we have a pKa of 50. You'll remember that the higher, let's say lower pKa is more acidic. So this is the more acidic one. Okay, so we can lose that hydrogen. Now you'll recall that the equilibrium is going to favor weak bases. So let's look at, this is really weird. And it's unworkable. Okay. So let's take a moment to look at the acidity of acetylene and terminal alkynes. Acetylene, we're talking about acidity, we're talking about the ability to lose this hydrogen right here. And the pKa for that hydrogen is about 25. The pKa for this hydrogen on the acetylene, on the ethylene, is 44, and on ethane, plain old vanilla ethane, is 50. You'll remember that a low pKa means it's more acidic. So it's easier to lose this hydrogen than either of the other two. The reason for that is that we have an sp hybridized carbon here, and that helps to stabilize that negative charge. It has more S characteristics to it. Okay, so if we look at the equation I've drawn here below and we figure out what we've got a base here, and this is our acid, and here we have our conjugate acid and our conjugate base. The reaction that's going to happen here is that the base here is going to act as a nucleophile. We've labeled it as a base, but it's going to attack that proton, and the electrons joining the proton to the carbon are going to go back and live on the carbon. Now if we look at the pKa's, we see that the pKa for this is 25, we already said that. The pKa for ammonia is 38. So this is a stronger acid, and it's going to be more successful at getting rid of its proton than is the ammonia. So the reaction is highly favorable in this direction. We can also look at the bases and see that this is the more stable base. You can either look at the pKa's or you can compare bases. Both of those systems work. But if we look at hydroxy, again, this is our base, and this is our conjugate acid. This is our acid and our conjugate base. What's going to happen here is we've got electrons on that oxygen that are going to attack the proton. The electrons joining the proton to the carbon are now going to go and live just on the carbon. And it will be stabilized because of the sp character of that carbon. If you refer to the table of acids in Chapter 3, you'll note that only hydride and an amide and an alkane with a negative charge are strong enough to deprotonate a terminal alkyne. Okay, so is the base strong enough to deprotonate a terminal alkyne? Well, this is the aforementioned amide, and so the answer would be yes. This is going to be a negative charge on an oxygen with some other with the alkane stuff attached to it, but with the T-butyl, but I don't put that in there. But anyway, it's a negative charge on an oxygen, and this is not going to be strong enough. It has to be a negative charge on a alkane or a hydride or an amide. And the next we'll talk about the preparation of alkynes.